That's because the halogen is very electron rich and repels the other electron rich nucleophile, and also because of some more complicated orbital considerations. But we know from experimental data that it always does this because of the way that the stereochemistry gets inverted. You notice this carbon has 4 different groups attached. R1, R2, R3, and a bromine. So that's an asymmetric carbon, as long as all 3 R's are different. When that nucleophile comes in and pushes out the leaving group from the opposite side, here's the scenario, the nucleophile starts to bond as the leaving group starts to leave. So there's a point where you actually have 5 bonds to the carbon, but 2 of them, these bonds are actually dotted bonds. They're sort of partial bonds, and illustrate a process where the middle point would sort of look like this, but not necessarily. So the transition state for this step would probably look something like this, where the nucleophile is partially bonded and the leaving group is partially left. And then as the nucleophile completes that and the leaving group departs, you have the so-called inversion of stereochemistry at that asymmetric carbon. Now be careful, this and what we started with are not mirror images. If this were a hydroxide ion, for instance, we'd be making an alcohol from an alkyl halide. Not only are they not mirror images, they're not even the same class of compound. The inversion refers to the spirit of the stereochemical change. And often, because nucleophiles have oxygen or halogen attached to them, the nucleophile is often the same priority as the leaving group in the R and S configuration. So this inversion often leads from R to S or S to R, but not necessarily. It could go from one R stereoisomer to a totally different R class of compound stereoisomer. They wouldn't be stereoisomers of each other. But you get the picture. This is a one-step reaction. Go back here. See if this will play out of here.
Is this all you put on the board so far? Yeah. Got here a little late too. You're recording too.
Primary halogenoalkanes undergo SN2 reactions, where the S denotes a substitution reaction. The N shows the reaction involves a nucleophile. 2 is the number of species involved in the slowest rate-determining step.
I'm recording the video, look.
A nucleophile is an electron pair donor. It is attracted towards species carrying a full or partial positive charge, with which it can form a dative covalent bond. Consider the reaction between a hydroxide ion in solution and bromoethane. Both reactants are involved in determining the rate of the reaction in a one-step process. The hydroxide ion attacks the carbon atom from the opposite side to the halogen atom. Because the bromine atom, A, is so large it impedes the approach of the smaller
This is
hydroxide
the
ion,
reaction
and
coordinate
B,
profile.
it repels the
following
negative
this.
charge nucleophile. The lone electron pair on the nucleophile forms a new dative covalent bond with the partially charged carbon atom to give an unstable transition state complex.
I look like a stalker.
The complex behaves like an umbrella blowing inside out as the bonds rearrange into a tetrahedral structure. A bromide ion, called the leaving group, is
British accent.
The transition state complex.
Echo. It's so trippy.
Okay, so that gives you some kind of a mental image, which is so critical, these things. And
That's gonna be awesome for my YouTube.
what's this?
Post it on YouTube.
Now, the other version,
SN2,
the other pathway to this reaction is the so-called SN1.
Tertiary halogenalkanes undergo SN1 reactions, where S indicates a substitution reaction is occurring, N indicates that the nucleophile is involved, and 1 indicates that only one species is involved in the slowest rate-determining step. In tertiary halogenalkanes, the small hydrogen atoms in primary halogenalkanes are replaced by bulkier alkyl groups.
Well,
Tertiary halogenalkane. The bulky alkyl groups do not allow attacking species to approach the central carbon atom.
it's beautiful.
Consider the reaction between 2-methyl 2-bromopropane and a hydroxide ion. It has a two-step enthalpy profile. The first step, the heterolytic fission of the carbon-bromine bond, has a high activation energy, EA1, and therefore determines the rate of the reaction. The first step involves only the halogenalkane and proceeds via a transition state complex to form a carbocation. The second step has a much lower activation energy, EA2, and hence is considerably faster than the first step. The carbocation reacts with the nucleophilic hydroxide ion via a second transition state to form the product 2-methyl propane 2-ol.
What kind of naming system is that? 2-methyl.
Transition state. Carbocation.
Putting my commentary on here.
EA2.
So in essence, a reaction.
I wonder if I could see the board.
The limiting step is the only step that it has.
Right, you have only one step, that has to be the rate controlling step. But in the SN1, it's the formation of the carbocation that controls the overall rate of production of the substitution product. The second step is faster than the first. The difference between the two mechanisms is only important, remember, when the carbon attached to the leaving group is asymmetric. Then you get inversion with the SN2, racemization with the SN1. The SN2 is better because it has a predictable single stereochemical outcome. That's called a stereospecific reaction. You can predict the stereochemistry of the product, and it preserves any optical purity that you have in the starting alkyl halide. So if you design the whole thing carefully, you can make a specific stereoisomer. But to the extent that it goes through the SN1 path, and they are somewhat competitive, it's going to racemize and destroy your optical purity. Remember, racemic mixture is the worst case scenario in terms of optical purity, 50-50. Now, there are ways of controlling this. The first is out of your control, really. Is the alkyl halide primary or tertiary. Primary favors the SN2. Tertiary favors the SN1. So in a black and white scenario, primary alkyl halides substitute primarily by the SN2 mechanism and tertiary by the SN1. The secondary, of course, is a gray area in between. So don't worry so much about all the factors that control this balance between SN2 and SN1. A lot of the discussion in the book is about that. Just remember primary SN2, tertiary SN1, and the reasons why. The primary is the one with the least steric hindrance around the leaving group, so that backside attack is very viable. And on top of that, it's not going to do the SN1 thing because primary carbocations are the least stable of all of the carbocations. So primary alkyl halide doesn't have anything to do with the SN1 carbocation, and it's wide open for the SN2 substitution. The tertiary halide is the opposite. It's too sterically hindered for the SN2, but it does form a tertiary carbocation, which is the most stable of all of the carbocations. So they're not really competitive. Most of the story is in the nature of your alkyl halide that's being substituted. And that's not under your control. I mean, if you have to substitute a tertiary halide, you can't just put another one there. That's silly. So that's out of your control. But a lot of things are under your control, like temperature and polarity of the solvent and catalysts, et cetera, solvent nature, et cetera. So there are a lot of things that can be done.
Are those activation energies specific for the SN1 and SN2 reactions? Like SN1, those two activation energies?
Well, any two-step reaction has two activation energies. Remember, there are tens of thousands of reactions that we know of, and some of them are one-step, some of them are two-step. If it's one step, there's just one activation energy. If it's two steps, there are two. And the first one could be rate limiting, or the second one. It just depends on the reaction. So no, they're not specific to this alkyl halide chemistry. And they're general for all reactions. And the issue is whether it's a one-step or a two-step process with an intermediate unstable product. It's a mixture as you look at reactions. Okay, so with these nucleophiles, all you have to be able to do for substitution is write the expected organic product. And this is the main way that reaction questions are presented on an exam. So you might see things dry out super fast. And sodium hydroxide reacting with benzyl chloride, which is a primary alkyl halide. And the question is, what's the expected organic product? Now, this reaction isn't balanced, and you're not being asked to balance it. There may be some minor things left out, like temperature or solvent that's used. That doesn't matter. There's an expectation based on what you know about the chemistry of alkyl halides that would lead you to expect a certain result. For nucleophilic substitution, you'd have to recognize that this is a primary alkyl halide, which means nucleophilic substitution, and in fact SN2, but the question doesn't really ask that. It just says write the expected organic product. The nucleophile is the hydroxide ion. So you have to have that mental picture like you saw in the animation of the hydroxide ion attacking the carbon attached to the halogen and eventually substituting for the chloride ion as the leaving group.
What does that say, cyanide?
And your chloride ion, of course, could be bundled up as sodium chloride, or
Cyanide
you
ion?
could leave that out completely, because it's totally irrelevant from the viewpoint of organic chemistry. I'm not trying to make sodium chloride, obviously. I'm trying to make, in this case, benzyl alcohol. So that would be the correct answer for the expected organic product from this reaction. And it doesn't matter whether it was SN2 or SN1, because the carbon attached to the leaving group is not asymmetric. There's no configuration specified like R or S. So that's simply it. And if you had water here, you had to draw in the expected organic product, you would picture exactly the same thing as in the top reaction. The oxygen is donating a pair of electrons to form this new bond and pushing out the leaving group. But notice, very important point here, when we're using water instead of hydroxide ion, there's a charge problem. The oxygen in the water is neutral to start with. If it donates a pair of electrons to form a shared bond, so you remember the scenario, I have $2, you don't have any, and I share my $2 with you, I only have $1 now. I'm short $1. The oxygen is short one of the electrons that it used to have when it was neutral. So the oxygen has to develop a plus charge, a formal charge of +1. You've seen that before, H3O plus, a hydronium ion. You saw it freshman chemistry 1,000 times. This product is benzyl alcohol with the oxygen protonated. Now, oxygen is a weak Lewis base. And whenever you see a situation where oxygen is protonated and has a plus charge, feel perfectly free to just take that proton away. Now, where's it going? Well, there are lots of water molecules around, for instance. Just take it and move it to a water molecule, or move it to the chloride ion, whatever you want to do.
We need Ronnie as binoculars.
Because the intention here, of course, is to make benzyl alcohol, not protonated benzyl alcohol.
I guess I'll just guess.
So just move the proton wherever you want, as long as it goes to an atom that can form a bond to the proton, either water or a chloride ion. So I'm still making benzyl alcohol. I just have to do a little proton work here.
Is that whenever there's a coordinated, like whether it's a carbon or an oxygen, it's
Just an oxygen. Oxygen, protons attached, hydrogens attached to carbon are pretty strongly attached. An extra hydrogen on an oxygen is very loosely attached. You know that water is not really considered to be a base by most standards. Organic chemists consider water to be a weak Lewis base. So if you put, say, HCl in water, the protons dance all over the place from one oxygen to another. They don't sit on an oxygen very long. This is a very weak and loose association. So anytime you're looking at a protonated oxygen and it's confusing you, just throw the proton away. It's going to go out to another basic atom. So that's still making benzyl alcohol. Doesn't matter whether you use hydroxide ion or water, except that the hydroxide ion would do this faster. and you'd be more inclined to use
Stuff I want to learn.
hydroxide.
Make alcohol.
The bottom reaction is one your book would refer to as a solvolysis reaction.
This is important stuff.
Because what you'd be likely to do is take benzyl chloride and dissolve it in a large amount of water. So the solvent, so to speak, for the reaction would also be the nucleophile. When the solvent is the nucleophile, it's called solvolysis. When the nucleophile isn't the solvent, it's called nucleophilic substitution. And it's often that the nucleophile is not the solvent. But particularly when we're talking about water as the nucleophile, or just plain alcohols like methanol, that tends to be introduced not as a reagent, but just as a ton of solvent molecules. So alcohols and water are what your book talks about in terms of solvolysis. But don't be thrown by it. It just means that the concentration of water is enormous. And that has consequences. It pushes the reaction favorably to the right, but it also confuses the kinetics, because the concentration of the nucleophile can't be measured. You know, if it's a ton of water and a few of the water molecules react as nucleophiles, the concentration doesn't really change. So don't be confused when you read the book when it says that solvolysis follows pseudo first order kinetics. It only seems like the concentration of alkyl halide matters with the rate. But that's because you can't change the concentration or measure the concentration of the solvent. There's too much of it. Okay, so the same thing would happen with alcohols. This is the sodium salt of methyl alcohol. It's called sodium methoxide. Now, if you parse out that name, sodium methoxide, parallel it with sodium hydroxide. NaOH, sodium hydroxide, NaOCH3 is sodium methoxide. The names just go like that.
Alcohol, meth.
And that works the same
Love this
way. We have a reaction like this. Just take the nucleophile, which is the O minus, and bond it to the carbon attached to the halogen. And you've substituted the bromide ion for the methoxide ion. Classical nucleophilic substitution. It's a primary halide, so it's probably SN2. If this were a tertiary halide, and you were to write a substitution product, you would have to assume that it went through the SN1 mechanism. I mean, that does operate. To whatever extent substitution occurs for a tertiary halide, it pretty much has to be SN1. But it doesn't matter, because this is not an optically active compound. Now, if you took the same nucleophile, and you reacted it with pure R 2-bromobutane. You know there are two stereoisomers there that are enantiomers, the 2R and the 2S. If you just had the 2R and were asked to write the expected organic product, you would have to include the stereochemical change, which would be that this carbon would invert its configuration. Now, what I'm going to do is replace the bromine with an OCH3. Notice I'm not writing sodium bromide as the byproduct. I don't care about that. You can write it if you're happy doing that, but I'm not looking for it. So this is the classical substitution, but what about the stereochemical change? Well, you could draw wedge and dash line figures and have the nucleophile invert the configuration of the correctly drawn R stereoisomer. But in this case, you'd be wasting your time because you can see that the bromine, which is a priority 1 substituent, is replaced by another substituent that's also priority 1. When that happens, which is actually fairly common, the R becomes S. Because the priorities are still intact. And if the stereochemistry is inverted, then when you work out the stereochemistry, the priorities would lead to an S configuration. So again, the 1, 2, 3, 4 assignments are intact in the product, and so the inversion produces the mirror image of the R, which is the S. But that product and the starting alkyl halide are not enantiomers. They're not even in the same class of compounds. One's an alcohol, one's an ether, the other is an alkyl halide, alkyl bromide. So in simple cases like that, you can easily keep track of it. To be certain of this, you could also draw three-dimensional, you'd have to draw the 2R, 2-bromobutane, in a stereo drawing, and then do the inversion the way you saw it in the animation, and then determine the stereochemistry of the asymmetric carbon in the product. In this case, it would go from R to S. So inversion of configuration, but retention of optical purity. Let's say it's 100% R. As long as it's SN2, it's 100% S. If there were some molecules reacting through the SN1, that would produce a racemic mixture of the R and the S product. And you'd see that lowering the optical purity. So if you got 75% S and 25% R, that would suggest that some of the molecules are reacting through the SN2 and some through the SN1. That would be unfortunate, but that's just the reality of the reaction.
Were you able to see that?
Configuration
Were you able to
and
see
retention of optical purity.
I'm blind.
Now, if it's a solvolysis with an alcohol, very important to have this animation in your head. The nucleophilic oxygen of the ethanol displaces the bromide ion, and you get this replacement of the leaving group by the ethyl alcohol molecule. Now, because you started with neutral ethyl alcohol and what's probably a solvolysis mode, you have an extra proton on the oxygen. So I'm just going to take it off, throw it out into solution. There's my ether, in this case diethyl ether, and I've circled the OCH2CH3 just to emphasize that that is was the nucleophile. Now it's replaced the bromide ion leaving group. if this were cyanide ion, let's say potassium cyanide, all you have to recognize with cyanide ion is that the carbon is where the negative charge is, not the nitrogen. Cyanide ion is nucleophilic from the carbon. It's actually a carbanion ion, negative charge on the carbon. And through that animation, cyanide ion bumps out the chloride ion to give you your substitution product.